So it's, of course, a great pleasure for me to introduce Jérôme GIOVINAZZO to you today. Jérôme started his scientific career with his PhD in the middle of the 1990s at IPHC in Strasbourg under the direction of Christian Millet. He worked on proton-rich nuclei, mainly the beta delayed proton emission of medium mass nuclei in the mass 70 region, 70 to 80. After his PhD in 1997, he moved to Bordeaux, to the CENBG lab, where he is still today. He is today the head of the exotic nuclei group in Bordeaux, with 8 permanent people, 5 postdocs, and 5 PhD students, if I counted correctly. His main work today is on weak interaction studies and exotic radioactivities. This is what he will present today. His work on two-proton radioactivity, notably with a new detector he developed together with his collaborators and technical departments in different labs. This ACTAR TPC device that he already used successfully in 2 or 3 experiments at GdR. And the topic of today is probably his main research activity as of today, two-proton radioactivity. So, Jérôme, it's up to you.
Okay, thank you very much for this introduction, and I'm quite proud to present you this. And I have to say that I'm proud that Bertram introduces this work, because I mean, he's somehow the leader of that. So it will be about this story of the two-proton radioactivity. Of course, it will be about radioactivity, about proton emission, and so on. So the outline of my talk is the following. So first, I will talk about the radioactivity decays on the proton-rich side of the table of isotopes. So I used to say proton-rich. I know people prefer neutron deficient, but it's the same. This will be just a short introduction. Then I will come to describe what is this process of two-proton radioactivity. And the main part of my presentation will be about this game between a theory and experiment, and the progresses looping from one to another. And just I will end with the last topic, which is a bit of an advertisement. It's a bit off the main topic of this presentation, but it's part also of the developments about this topic, presenting this new tracking device that is ACTAR TPC, which will be used also in that context. So let's start with this question about the radioactivity on the proton-rich side of the table of isotopes. Of course, it is about radioactivity. This is not a new story. 120 years ago of radioactivity history. But I will not go into detailed introduction on that, because there was a very nice presentation from Wally in November 2020, and I really invite you to see her presentation about that, where you will find all the details since the beginning of this story. We are talking about radioactivity. So what it is, this is simply the spontaneous transformation of the atomic nucleus in order to go to a more stable system. And this is like any system in physics. When the system becomes more stable, it's because it releases energy, and the energy is related to mass. So the stability is intimately related to the mass of the atomic nucleus. And if we look at the table at this picture, which represents the atomic masses in the nuclear chart in the table of isotopes as a function of the proton number and neutron number, this is the picture we get with the valley of beta stability at the center here. And in order to for the system that is the atomic nucleus to be bind together, then fraction of the mass of individual component is used to bind the system all together. This is a fraction of mass for binding, and this is called the binding energy or the mass defect, because the mass of the whole nucleus, of the nucleus itself, is lighter than the mass of the individual constituents. And this binding energy was described by the relation from Bethe-Weizsäcker, and this was already presented in the talk from Miguel Marquez in December, with this parametrization here of the binding energy. And here I will be interested in this term, which is the symmetry term, the difference between the number of neutrons and the number of protons, that is squared, and that is responsible for the shape of this mass plot when going from one side to another, to the other side, this parabolic shape. And since we have more mass or more energy in the sides, we can gain energy going back to stability, and this is the beta decay, beta plus or beta minus, of course, with the emission of light particles. And so the further you go, the less stable you are, and at some point, because of this sign, you reach a limit where this binding energy becomes negative, and then the system is not bound anymore with respect to the nuclear forces. And now I propose you a small trip going from the stability to the drip lines and look at the radioactivity process that occurs there. And if you are close to the stability, so not far from these tables shown in black arrows here, so there's a little excess of protons with respect to the number of neutrons, and then here, the protons will be in the nuclear potential, in the potential of the nucleus. They will be a little bit higher in energy, so the system can gain energy changing a proton into a neutron. This is the beta decay, and we go from one state to another state with lower energy. When we are close to the stability, the energy available, the Q value here is quite small, but when we go further from stability, this Q value will increase, and this gain of energy will increase also. Then this window will open, and we can populate higher energy state in the daughter nucleus, but not high enough to eject. It's a system that has too many protons, but not enough yet to eject protons. And this allows to make a different tests of the of the atomic nucleus, like spectroscopic studies or even test of the weak interaction, which is responsible for the beta decay. If we go even further, then this Q value still increases, and the proton separation energy will decrease, and we can now populate high energy states in the daughter nucleus of the beta decay, and these states can also then emit protons because they are above this emission threshold. And this beta delayed proton emission is very interesting for study of the structure of the nucleus, but also for nuclear astrophysics processes and so on. And it's this proton emission which is this is a way of measuring also very excited states, as the proton can be measured quite easily. Going even further, then is open the channel for multiple proton emission after beta decay. We start to go into complex schemes, and here you see that you have the weak interaction playing here, the electromagnetic interaction playing here, and the nuclear strong interaction playing in the proton emission. This kind of complex decay schemes are often the only way to access information when we are very far from stability. And if we continue our trip and we pass this limit where the binding energy becomes negative, then we reach some nuclei here where the proton separation energy becomes negative. We have this kind of scheme here. So these last protons, they are not bound anymore with respect to the strong interaction. Of course, the beta decay is still possible, but here we reach the drip lines, and the last protons are unbound. And this is what we will be interested in here. And then I will come to the second point, which is to describe what is the two-proton radioactivity. And this is not a new story either, because this was proposed already in the 60s, so more than 60 years ago. And the first description of this phenomena was proposed by Goldansky, but actually there was already a mention of this process, but only a mention 1 year before by a Russian theorist that was called Zeldovich. And a few years later comes the first theoretical description of this decay process, and here it's the one-proton and the two-proton radioactivities that were described. It's 10 years later than that the first proton radioactivity has been observed experimentally, but the first observation is from an isomeric state here in the cobalt-53, which is the first case. But to observe it from a ground state, the ground state proton radioactivity, we had to wait more than 10 more years, and this was observed in odd nuclei at GSIs in two cases, lutetium 151 and this nucleus here. In the mass 147, and to observe the two-proton radioactivity, it was 40 years after the first prediction, in the years 2000, in the beginning of the years 2000, with two experiments, one that was performed at Ganil and another one at GSI. And then you can see that it took a lot of time going from the first theoretical predictions to the experimental observation. I will come a little bit to that later. So what happens when we are at the proton drip line? So I come back to this region where we are where the binding energy has become zero because it's too many protons, and the last particles are not bound with the nuclear interaction. And if the scheme was like that, so where we cross the binding energy zero, so this is the more closer to stability, and we are further from stability. Here we cross the binding energy zero, so this would be the drip line. And after, beyond this drip line, the last particle is not kept inside the nucleus, and the nucleus cannot be created, and its existence time is in the order of the time scale of the motion of the nucleon inside the nucleus, which is typically the order of 10 to the minus 20 seconds. This is a simple picture, but since we are on the proton-rich side of the table of isotopes, there is another effect that occurs, which is the Coulomb barrier, which is a potential that is created by the positive charges of all the protons in the nucleus. And because of this proton barrier, a proton can be kept inside this potential for a while. And of course, after some time, because of the tunnel effect through this barrier, the proton will be emitted. And this can be a simple description of the one-proton radioactivity that can take place for nuclei with an odd number of protons. And now if we look at another tiny effect but important in nuclear physics, it's the pairing effect. The pairing effect is the gain of stability of the atomic nucleus when the number of protons or the number of neutrons is even. The nucleons will group by pairs, and the system gains stability. This can be seen here on the stable isotopes, because you see that my mouse has a problem. I have a technical problem, sorry. My mouse is not moving anymore. I will. I really have a problem with the mouse. So here you have odd even effect with more stable isotopes in the case of even number of protons and neutrons. And you see it also at the drip line with this shape here, where the stability goes further for an even number of protons. So in our previous picture here, what will happen here is that because of this even number of protons, we will gain energy here. And because of that, together with the Coulomb barrier and this sparing effect, the two-proton radioactivity can occur, which means this state is stable with respect to the emission of one proton. It cannot emit one proton, but it can emit two protons. It will gain energy in emitting two protons, which gives this picture here where the two protons can be kept inside the nucleus and they have to be emitted simultaneously. And they cannot be emitted independently one of the other. And this is what we call the true two-proton radioactivity that it is about in here. So there are many interests in studying this process because, of course, as you see, it's something that occurs at the drip line and it's related to the mass of and the limits of this table of isotopes. And this can be addressed through the Q value. Of course, it's related to the energies of the levels involved, the half-life, and we will see also that the wave function and the level configurations of this nucleus will play a role like that. And this effect is also possible because of pairing. And it's a very interesting tunnel effect. And as far as I know, it's a quite unique case of tunnel effect where you have a strongly correlated system inside and a system that is completely unbound outside, because this two-proton subsystem is unbound outside. This helium-2 does not exist by itself. It's only inside the nucleus that it exists. And these protons, when they are emitted, they carry some information of this correlation inside the nucleus. And this process will mix two aspects of nuclear structure and nuclear dynamics, which also makes it a quite complex process. Now, if we go to the work that has been achieved during these 60 years, let's start with the initial predictions by Goldansky, where he used a quite simple potential model here. And you have helium-2 subparticle inside this potential that will be emitted by after a tunnel effect. But the game was here to calculate the penetration for the helium-2 or for individual protons and discuss the splitting in the process of emission. This was the first simple description. And what is interesting here is that from the prediction at that time, he already predicted that the most favorable region to observe it would be the mass equal 50, A equal 50 mass region in those cases here. And he was he was quite precise already at that time. So how do we search for? We have this prediction, and now we want to observe it experimentally. So we will search for candidates. So we need to find some nuclei for which the transition energy for two-proton emission is positive and for one-proton emission is negative. This is related to the mass difference of the parent and daughter nucleus, but nothing is known about their masses. So we have to rely on mass predictions. And from the different mass predictions, this gives the Q value. And taking a simple tunneling model of helium-2, there is a relation between this transition energy deduced from mass and the half-life, which is a kind of you see that here you have a logarithmic scale, so it's very quickly decreasing half-life with the Q value. And here you have the example of nickel-48 with all the mass models that were available at the end of the 19th. And in order to be able to observe the two-proton radioactivity, the two value needs to be small enough so that the half-life is long enough and we can observe it. But if this Q value is too small, then the half-life will be too long, and then because of the competition with beta decay, we will not observe the two proton because it will be the decay will be dominated by beta decay. So in this A equal 50 mass region, we have quite high enough Coulomb barrier to keep the protons inside. And then we expect there some half-life in the order of the microseconds to few milliseconds. So this is where we focused the search for candidates. And here you have a map showing some of the best candidates to look for this. Now the problem is we are at the drip line. It's nuclei with very short half-life, and they are extremely difficult to produce. And this is why it took so much time to be observed. To produce this nuclei, we need accelerator with nuclear reactions to produce unstable nuclei. But not all reactions will work. For example, these nuclei are out of reach for reactions like transfer or charge exchange, fusion evaporation, or induced fission. They could be produced in with other technique, with other reactions, like the target spallation, which is associated to ISOL technique, like at CERN ISOL, for example, because here you have a high energy projectile, usually like protons, that you send on a sick target here. And here you will produce a lot of exotic stuff. But the problem, you need to extract them from the source. And this extraction takes time. And after extraction, you need to separate them and purify them at low energy. And this takes time and it's too slow. So these nuclei cannot be accessed with this technique. They can be produced, but you cannot study them with this technique. So the only solution is the projectile fragmentation, where here you have a high energy heavy ion projectile that you send on a target. But here it's the projectile will fragment and the fragments will go through the target with a high energy that you can separate in a fragment separator, and you have to separate it in charge and mass, and then send it to a detection system to implant the fragments and look for their decay. And the experimental work took a lot of time because we needed the fragmentation facilities to be developed, and this started in the end of the 80s and a lot in the 90s with the GANIL LEAS installation. The LEAS separator is this one, and the fragment separator at GSI, which is here. And then also in the years 19th and 2000, the same type of facility at NSCL, at MSU, with the A900 separator and the RICAN and Big Rips facility. Here the separator is here, Big Rips. There are also now new developments with FRIP starting right now with FAIR and the Super FRS. I will not discuss these ones because I will they are not part of what I'm presented, but we needed all these developments on fragmentation facilities to be able to study this experimentally, to study these nuclei. And this is why the exploration could start. And the first result I will mention is the discovery of iron-45 in an experiment at GSI with 3 events that were identified here. And a bit later at GANIL, with this observation of nickel-48 with 4 events. So this was the beginning, but unfortunately in those experiments, we had no information of the decay modes. So the isotopes have been created and observed, but no information on the decay. I will say just a few words about nickel-48 because this one has a specific interest because it is the most proton-rich nuclei of the table of isotopes with 8 protons more than the number of neutrons, and it's the only one that is that far with that big difference, proton to neutron. In addition, it's a doubly magic nucleus, which makes nickel the only element with 3 doubly magic nuclei, which is of specific interest when we want to study the shell structure. And this nucleus that is really far from stability and quite alone is most likely bound because of these strong shell effects of this double shell closure. And it was also foreseen to be, because of all this, it was foreseen to be the best candidate for the 2-proton radioactivity. Now, after that came the first observation. And actually, two experiments could observe the first two-proton radioactivity, and both in the case of iron 45. And I will show you this experiment at Ganil, where we had a very intense beam of stable nickel that we sent on this fragmentation target, and then selected from all the fragments created here, selected in the least separator to end with a few tens of ions that we send in the detection device. All these ions that were created, they are shown here on this identification plot with the time of flight in the line and the energy loss in the detector. These are standard identification metrics. But concerning the nucleus we are interested in, iron 45, it's only few events per day. So you see that's not much. At the end of this experiment, we had 22 events of iron 45 that we could observe. And these ions, this iron 45 nuclei, they were implanted in a silicon detector. I mean, I say it's thick silicon detector. It's not that thick, but thick enough for when the decay occurs after the implantation, this nucleus that is highly unstable will decay, and it can decay either by proton emission or two-proton emission or by beta decay. So it will emit beta particles and protons. But the protons, the detector is thick enough so that the protons, they do not escape the detector, and they leave their full energy in the detector. The situation is a bit different for beta particles because they travel much more in silicon, so they escape the detector with two consequences. First, they leave only a part of their energy in the detector, not the whole energy, and they can be detected in coincidence in in other silicon detectors. And this gives us the possible scheme for the decay of iron 45. On one side, a beta decay, but that will be followed by proton emission because this one is unbound with respect to proton emission. So beta 1p, beta proton, beta 2p, beta 3p, or p alpha, many open channels. But in that case, the proton will not go out, but the beta, yes. And in the other case, the two-proton radioactivity that we are looking for, but in that case, there is only emission of protons, and all the energy is deposited in the detector, and we should get a nice peak here, where in that case, we have a degraded peak. And this is exactly what we observed. And this is why I mentioned, I consider it as an indirect signature, because it's based on global observation. First, we've seen this peak here, and this peak is not in coincidence with beta particles in other. So this is the energy measured in the silicon detector, and this peak is not in coincidence with beta particles. Is a narrow peak, so not degraded by the beta pileup. But also, and what is very important, if this peak corresponds to the two proton to this state, this nucleus is also very exotic, and it will decay by beta delayed proton emission. And after, when we have the decay here, there will be a next decay of this one, and the half-life of this decay has to correspond to chromium-43, and it's exactly what we observed here. When we look at the second decay after the implantation of iron, and we measure the half-life of this second decay, we get this point, this value here that is compatible only with chromium-43, and this signs the two-proton radioactivity. So we had this observation of the two-proton radioactivity on iron 45, so both at Ganil and GSI, which has the GSI experiment had results that are completely compatible with the Ganil one. I do not come into the details. It's indirect signature because we do not observe the individual protons. We concluded to the occurrence of this process because it's the only scenario that can explain the measurement, the half-life, the Q value, and the daughter decay, and so on, and the absence of coincidence. So we found this two-proton radioactivity. But with that case, it's not enough to understand the process. And this work went on. And based on the same experimental technique, we could observe also zinc 54 with the same technique, the two-proton decay of zinc 54, have some indication for nickel 48 that will be confirmed later in some other experiment. I will show you later. And more recently, in an experiment at RIKEN, always with the same technique, we could observe the two-proton decay of chromium 67 that is here. I will come back to this nucleus also. But now, as I told you, we have a quite limited information for theoretical interpretation, because basically we have the half-life. Of course, we have the branching ratio, also branching ratio between two-proton radioactivity and beta decay, but this gives us the partial half-life of the two-proton emission process. So we have the half-life and the Q value that we measure. And now the idea is to try to understand this on a theoretical point of view and from theoretical models. This is not an easy task because we are dealing with systems that are unbound with respect to the nuclear interaction. And then the states in the continuum will play a role. And in addition, we have to treat this emission of the two proton as a three-body system, which is intrinsically difficult to solve. So the first theoretical approaches were based on simplified approaches. The first one was air matrix formalism using shell model wave functions and including proton-proton resonance. This was developed by Barker and Brown. And then there were some attempts to describe the process in the framework of the shell model embedded in the continuum to have this coupling to the states in the continuum. But as I say, these models, they do not include the dynamics of the emission. And as I said, the comparison is limited because basically we have one experimental value to compare, which is the half-life, knowing that in the models, the Q value is taken as a parameter. So basically we have the half-life to try to understand the phenomenon. Came also another model, which is called the three-body model. This one is a bit different because this model addresses the question of the dynamic, the emission, the dynamics of the two-proton emission, but it does not contain intrinsically the nuclear structure. And this was the kind of comparison we could do on the half-life with the different models. But an interesting point of this model that pushed us one step further is that this model can predict the correlations between the emitted protons, and it will between the angular distribution and the energy sharing of the proton. How do the proton share the energy, the available energy, and the pattern of the angular distribution? And the interesting point of this correlation patterns is, as you can see here, this is more really reflecting the angular correlation, not exactly, but that this pattern will depend on the inner structure of the emitting nucleus, on the wave function of this nucleus. So it's sensitive to the nuclear structure. And this was interesting, but now the question, if we want to go one step further, is how experimentally to measure this angular and energy correlation to access nuclear structure beyond the drip line. And then came a new generation of experiments that I call the tracking experiments to overcome this limitation of the standard experiment with silicon detectors, where we cannot see individual protons. The purpose of this tracking experiment is to measure protons individually to get access to this correlation, compare with this three-body model, and try to extract some structure information for this nuclei. And the principle is relatively simple. And the idea was to use time projection chambers. And basically, we replace the silicon detectors by a gas volume. And when the ion will stop in the gas volume, then the decay will occur, the two-proton emission will occur, the particles will be emitted, and since they are charged particles, they will ionize the gas, this gas volume. And this ionization along the tracks. Thanks to an electric field, we will drift it towards a collection plane here that will measure the projection of this ionization signal, so the projection of the tracks of the emitted protons. And the third dimension is given by the drift time. And two devices have been developed. One that was developed at CENBG, a first time projection chamber based on a collection plane with a strips readout. And the second one was an optical time projection chamber developed by our colleagues in Warsaw. So the principle is the same, but here the ionization signal after drifting is converted into light and read by a CCD camera. And then these new devices allowed first for a direct observation of the process, and the first direct observation of these two proton tracks, and this was the first case here in the case of iron 55. This was in 2006 or 7. And then this was followed by the other cases, zinc 54. So these are with the CENBG TPC and these nice plots from the Warsaw, the optical TPC. This was confirmation that nickel 48 was also a two-proton emitter. And this experiment that was performed at NSCL by our colleagues, this allowed for the first experiment with good statistics about the two-proton radioactivity with 75 counts of two-proton emissions. And this allowed to build this angular and energy correlation distributions that are shown here, and to compare with the three-body model predictions. And you see that it's quite in good agreement with what with what came out of this model. And then these were pioneering experiment to study structure from this correlation and to try to be sensitive to the wave function of this nuclei. So we have one case with iron 45 and a few statistics in the case, very little statistics in the case of zinc 54. But if we look at this model and the sensitivity to the wave function, we can nevertheless deduce something about the orbitals involved in this nuclei, which is quite expected in the result here is quite expected in the case of iron 45 with a low contribution of the p orbitals. This is more questionable in the case of zinc 54 because here this contribution of the p orbitals is also quite low, while it's expected to be more. But you see that due to the very poor statistics, the uncertainty is extremely high. Nickel 48 would be an interesting case for that because it's doubly magic, so we would expect a pure configuration here, so a quite simple pattern with nothing here. But unfortunately, we don't have any experimental information on this nucleus. So, as I told you, we have two types of models. These three-body models, which has a good intrinsic dynamic description, and the models that have a good structure descriptions, like the ones developed by Alex Brown. And we played this game of building an hybrid model from both of them to take the best of each part, this good dynamics through the half-life of pure configurations and through the amplitudes of these various configurations from the structure point of view. And this is what we call the hybrid model. And if we look at the case we have here, we see that we have a quite nice agreement. So the process is more or less under control. And this would be a very nice thing. But the story did not end there because, as I told you, we measured another nucleus, which is krypton 67. And in the case of krypton 67, this model completely fails. And it fails from an order of 20 to 40. And this experimental observation was in 2016. And now the question is why this phase and how to solve this puzzling of the two-proton decay of krypton 67, how it was called in this paper that came a bit later. And to try to explain that, this discrepancy, there were two hypotheses have been proposed, and the first one was proposed by Grigorenko. As I told you, at the drip line, the masses are unknown. So we rely on mass prediction, which are quite uncertain, with large uncertainties. And the question is, what is the position of this intermediate state? And depending on the position of this state, we can have a transition between what we expect as a true two-proton radioactivity, if this is very high, and if this goes down here, we will move to a region where the decay will become sequential. So depending if we are located in this region, we are in a transition region. That could explain the problem of the half-life. And in the calculations from Leonid Grigorenko, depending on this resonance, what he calls the resonance energy in this intermediate state, depending on this position, it could explain this half-life, this experimental half-life that was observed. But then, how to look for this hypothesis? But if we are in this transition region between these two processes, in the case of the one-proton radioactivity, the energy sharing of the two protons will not be equal, because here you will have specific energies that will be favored, either here or here. And if we look at the sharing of the energies, fraction of energy of each protons, we should have something that becomes asymmetric, and we should be able to observe it in the energy pattern, in the energy sharing pattern. So this hypothesis was proposed in 2017, but there was a second hypothesis that was proposed by Wang and Nazarevich, which is the question of the nuclear deformation, because krypton 67 is at the beginning of this region deformation here. And they made some theoretical development with the gamma-coupled channel calculations and coupling to the core excitations. And they concluded that if you consider krypton 67 as spherical, you have a very large half-life. But if you take into account the deformation and the role of this G9 half intruder, then you can get something that is in agreement with the experiment. The interest of this gamma-coupled channel model is that it also predicts the angular and energy correlation. The angular correlations. And this is very interesting for us because it was calculated in the case of nickel 48 that is expected to be spherical. And this correlation pattern was calculated as a kind of, or this nucleus was calculated as a benchmark of the model. And they made the calculation for krypton 67 in the case of spherical shape or in the case of the deformation with the influence of this G9F orbital. So now we have several explanations for this discrepancy with two models. On one side, this gamma-coupled channel calculation, on the other side, the three-body model. But the predictions are a bit different. And if we take the case of nickel 48, we will have a different prediction for the angular correlations, with this one from the GCC and this one from the three-body model, where in the case of spherical pure configuration, we would expect nothing in this region, which is different here. Difficult to, so disagreement between the two models. This one has the advantage that it treats in a consistent way both the structure and the dynamics. So this is a strength of this model. But on the other side, we have seen that in the case of iron 45, this model was in good agreement. So we will have to discriminate between both of them. So nickel 48 will be an excellent test case for this. And then from that, we will address the problem of this krypton 67, measuring the angular correlation to see if we see something in agreement with this model, or to see if we see something which is in agreement with this transition situation between two-proton radioactivity and sequential emission through the energy sharing of the for the two-proton. And this now it's on the side of the experimentalists to do the job. And for this, the idea is to go for new tracking experiments, and this will be done with ACTAR TPC. And these experiments are already foreseen. And the measurement for nickel 48 should have been done in 2020 at Ganil, but unfortunately, with this world situation, sanitary situation, the experiment had to be cancelled, and so it's now planned to be done in spring this year at Ganil. And then try to do this same correlation measurement at RIKEN for Krypton 67. So these experiments will be done with ACTAR TPC, and this drives me to the last part of this presentation, which is a presentation of this new device. And this was built in this ACTAR TPC collaboration that was the initiative of initially a joint effort from the Maya collaboration from Ganil and co-workers that were using time projection chamber for nuclear reactions, on our side where we were using time projection chambers for ion stopping and decay measurements. And the idea is to build a new generation tool that can address a large physics case for nuclear physics, from structure to decay studies and so on. So this was funded by the development of this detector was funded by the ERC at Ganil, and we had also some funding from Région Aquitaine. So what is the principle of this detector? Actually, so it's the same principle than the previous TPCs I've shown you. But here the idea is to have a full 4D detector, full 3D tracking plus energy measurement. So when you have a charged particle traveling into the gas, you have ionization of the gas. And if you collect this ionization signal on a path plane, you have a XY picture image of this track, of the 2D projection of the track. Now, on top of that, you have the time projection chamber principle, where the third dimension Z is given by the drift time. And if in addition, this time, the signal along time is digitized, if you have a time sampling on each of these pixels, then you will have a full 3D voxelization of the charge along the ionization along the tracks. So a full 3D reconstruction of this charge where you can analyze the tracks themselves, the trajectories, and the charge of the energy deposit from this particle. So this is the basic principle of ACTAR. Of course, the reality is not that simple, but and if here I just present the main component of the device. So you have a gas volume here with a drift cage that is responsible to have a nice electric field for the drift of the ionization signal towards the path plane. There was some important developments on the path plane, and here we will we have a detector with 16,000 channels, 16,000 pads for this 3D reconstruction. And for the time sampling, dedicated electronics has been developed. I will not come into the details. This was the role of the GET collaboration. And this is an electronics that was developed for the readout of these 60,000 pads. So this detector is now a reality. And after commissioning in 2017 in active target mode on this reaction. This was the work by Thomas Roger and the thesis of Benoît Mauss. This was with the first path plane, and then the first physics campaign started in 2019 with two experiments, one in active target mode on giant resonance, experiment from Ricardo Abe and with the help of Mein van den Broek. And another experiment that here is more our focus here. This was the first implantation decay experiment with ACTAR. And this experiment was addressing the proton radioactivity of isomeric states in nickel 54 and cobalt 53. I remind you that this one was the first observed proton radioactivity from an isomeric case. Sorry, from an isomeric state. Now I will mainly focus on this one just to show you what could be achieved. So the interest of this study of this emission of this 10 plus of the decay of this 10 plus isomer is related to isospin symmetry with iron 54. I will not go into the details of that, but here we are also in the region of n equal 28 for shell structure studies, and also for a shell model coupled to continuum. What is interesting here, we have branches, proton branches that are open with very high angular momentum. So this is a very reduced, sorry, unfavored transition. And these are the transition we are looking for, with a similar situation in the case of cobalt 53. So the problem in that case is that it's a very short half-life. So we will implant the ion in a detector, and then the decay of the protons comes very shortly after. So this is impossible to measure with a standard silicon technique, with a solid stopper, because the high signal, the important signal from the implantation, from the ion implantation, will completely hide the small signal of the proton on top of it. The scale is 1 to 1,000. So an experiment that is impossible to be done in a solid detector. This is why we used a time projection chamber, because here, if the proton tracks is separated from the ion track, we can see it, and this is exactly what we did. And I will show you a small animation with the principle of this measurement. And here, the ion is implanted, the ionization signal drifts, and after some time, the decay occurs, and we will have the projection with different tracks, so we can see the protons. This signal is much smaller than this one. And here, this time difference that we can measure by the time measurement with ACTAR will give us the half-life. So here we have a 4D imaging because we have the track and the track length and the track and the time. And this is what we did for all the in this measurement. These are here real events that we measured. We had about 2,000 and a few hundred proton events, and from the track lengths here, you see the two track lengths that corresponds to the two proton energies that are clearly observed here. And the time difference between the ion track and the proton tracks will give us here the half-life, this curve, this exponential curve, which is the half-life. Okay, in that case, we had the collection plane, the path plane had a few problems from which we could not have a direct measurement of the energy. And here the energy is measured through the length of the tracks. So we measure the length and the time difference, which give us the information. And that's what we could do with this new device. And now the idea, this gives us very lot of confidence for what we want to do now with two-proton radioactivity, which is basically the same type of observation for nickel 48 and will start or it doesn't start. Oh, sorry. Oh, my animation doesn't want to start. I don't know why. So you will not see my animation that does not want to start. I don't know why. But the idea is to make this measurement now for nickel 48 on chromium 67 for the two-proton radioactivity. And here, to summarize, this is the timeline of all this work that has been done on the two-proton radioactivity from the first theoretical prediction in the 60s the development of fragmentation facilities, the discovery of these very exotic isotopes, first indirect observation of this two-proton radioactivity, then the tracking experiments, and with all the theoretical models that have been developed during all this time. And now we are here. We had this COVID problem last year, and now we continue this game. And this is where we are now. And I thank you for your attention.